Hi.
Okay, so my suggestion is if everybody who's in the project have to stand over to the inside, and then if we put the demos. So what we're going to do is use the chairs around the microphone back.
No,
Okay, we're going to be in a couple of minutes. We're still waiting for a couple of the reviewers. How are you?
How are you, Jeremy?
fine.
I'm all right. I'm good.
All right. We are already live.
You're alive.
We are already live streaming,
All right.
broadcasting.
I'm going to get out of the way. Oh yes. So can you post us the Google address?
Sure. I think I already gave it to you.
So if you've got a phone and you want to get on the network, you can actually watch it on your phone. Because we've got multiple windows here, so you can flip between the windows at your choice rather than relying on us to flip on Windows for you. So Carlos, if you've got it as well, do you want to try that, or are you? Okay, you don't have network. So. So,
Okay, they're back.
come in. So we've got 3 seats.
Hello.
So we've got seats there. And we've got another one.
It's only one.
Yeah, it's all one.
You're okay. So, all right. So let's Carlos say hello.
Yeah. Hi, Cecile. Hi, Seth. Hi, all the reviewers.
Okay. So
Sorry, could you just turn down the camera a bit because I don't see the reviewers?
I think you probably still won't.
Oh,
Yeah, there you go. And Cordelia. Okay. So Seth and Antoine are that way.
Hi, Seth.
Okay, so we're going to start with tactile exploration. So, Carlos, show is yours.
All right. So we're going to show a practical implementation of the theoretical advances in Word Package 3, introduced earlier by Claudio as the GP Atlas RRT algorithm. This is Vito behind me, with some modifications. There is a IMU-based sensing glove on the left hand. This is required for the robot to know how his hand is configured for purposes of in-hand object segmentation. And on the right arm, there is the exploratory probe with a force torque sensor behind the tip, which allows us to recover contact information. So both gadgets were presented in previous years, and now they are integrated here in this demo. Now the algorithm can handle any arbitrary shape, unknown shape of any object. We will be delighted to show you the exploration of several different objects, but we are constrained by time. So I would need the reviewers to agree on which of these objects they would like to see on the demo. In this demonstration, we have a green spoon, a white colander, and a red container.
Yeah, I was going to say
Green spoon.
green spoon.
Green spoon. Yeah, he's really happy with that.
Good. Excellent choice. Now, let me put you on Vito's shoes. Imagine you are given an object an unknown object, like I just did. This is unknown for him. And then you need to you're allowed to have a glimpse on the object, which is done from this viewpoint only, this camera over here. And it's doing that right now. And then you need to rely only on your tactile skills to recover the shape. But you recall, and you don't have any clue of the texture, color, or any similar shapes of that object. And you need to do it without crashing. So this is really hard. Right? So,
Carlos?
Yeah.
What should I show them?
So now you have one of the view is the GP Atlas RRT algorithm working live right here, right now. Is this one here? Let me see.
Yeah, we've got that.
Yeah, present to everyone.
So we can see we've got the colored points on screen.
Yes. So the blue points are the initial partial view, the glimpse that we allowed the robot to have. And you can see the charts are the green disks that are the exploratory path that we planned for it. So each exploratory path can end up in a contact or not contact point. Both are useful for the algorithm. So we can update the internal representation with this information and continue the exploration. In the view, you have in light blue, you have the contacted points, which we already have 3. And in red wine, there are the not contacted points. So now Federico is turning the view around, so you can have a view of the current GP Atlas RRT algorithm. Now the procedure is repeated until a threshold for the uncertainty is achieved on the predicted shape. Now there is this view that I'm showing right now that you have the predicted shape with the uncertainty associated to this prediction in colors. From green to red means more uncertain, side by side with the ground truth. So in the right you have the ground truth because we knew when we had prepared the 3 models. So we're showing the ground truth, and on the left side there is the predicted shape with the associated uncertainty. Now, in other words, the algorithm finishes when all these points are green, which would mean that the predicted shape is very close to what it should be in reality. Now, converging to a very good predicted shape in this case is very slow due to the fact that each exploratory path must be collision-free and reachable by both arms. So only those that are collision-free and reachable by both arms are executed. So that takes time in this case. Now, I'm going to leave Vito here in the background doing his thing. We can check back later at which point it is with the exploration. And let's open the microphone for questions for now. Thank you very much.
Okay, so questions on this. You're going to see it. It's going to do the exploration. It's going to take a while, so we're going to let it brew. But we want to know if you've got anything you want to ask about it right now. What kind of objects can it model?
The Gaussian process modeling can handle arbitrary shapes of any topology. I mean, it's a Gaussian process regression of certain sample points. So it could have also holes or convex. The only thing is that it takes time for this, in this case, in the real implementation, for this to converge to a really good shape. But in simulation, I think Claudio showed earlier in the simulated poking.
So the question that Cordelia is asking is about as it were, the resolution. So what's the minimum size of the objects?
That's user predefined or high-level preset. We set a threshold for the variance for the uncertainty of the predicted shape, and the algorithm continues until that threshold is achieved for the shape. That's one of the advances with respect to other approaches in the literature.
Okay.
Any other questions?
When you reconstruct the shape from the sample point, implicitly underneath is some sort of grid that affects the connectivity of the data points within the object. Is that true? I never managed to.
I think he can't quite hear you.
I still don't manage to understand the underlying representation of the shape.
Yeah.
So if there's a Gaussian process, then you need to know something about the mean, and I'm not sure how you represent the mean. You have a bunch of data points.
I couldn't hear you well the last part. I know it's something about the representation, but I couldn't hear you well.
Well, actually, I can answer.
Okay, so Claudio's going to try and answer.
All right.
The Gaussian process is an approximation of this function. And you know the implicit function is zero when is on the object. So what you do a grid, called sampling grid.
So you're sampling.
Exactly. And when you get a point, no, you just go with the point. But the Gaussian process, you can say, okay, this is a new point, and I want a prediction on this point, on the value of the function, which is going to represent the implicit. So if the value is close to zero, that is a point that we accept and withdraw in the model. If it is far from zero, means that it's outside of the object and it doesn't belong to the structure. But also, since we have the variance associated with the prediction, we can draw these points with a different point.
If this is the part that is one of the things that if I change an implicit function a little bit, I can change the global topology.
We will have another object.
How is this handled?
Because it is being trained on the visual input data that we got at the beginning, and then it's refined by the so basically it learns over time the shape of the object.
So, vision data study for the role.
Well, it just gives you a lot of points because you could start without vision and start poking the object, but it will require. It obviously gives you a better hint if you can reason, because with Gaussian process you can start with random Gaussian process, which are function in the workspace. They are randomly generated with their zero mean. Then you start adding 1 point, and what you want to see is those Gaussian processes which are a set of functions that are growing, that are legal according to the Gaussian process variance and mean. What happens is they will converge on the new point of view. So that changes the variance of the Gaussian process. Then you have a new point and you see converging. Obviously, when you don't have observation, your variance.
Your assumption that the structure imposes constraints
is actually the kernel that we're using, because the covariance is generated in a way that is a relation between inputs. Right? So if you are thinking that in the real world, things are smoother and a closer point should give you closer prediction, then what happens is if I got a point that I never saw before, but is very close to my training data, I'm assuming that the answer should be very close to what I've seen in the data. Obviously, this depends from the kernel. The kernel which chooses the hyperparameter, which obviously change also this behavior, how close I should, compute this correlation. What we are using is the thin plate. The plate has a huge role in this task because it helps to define implicit function. Because it's a volumetric representation.
And so it represents a prior.
Yes. In a sense, the prior of how the work works, right? Exactly. How correlated are the point, how I can trust my training data when I do prediction.
And if I know there are some shapes that you cannot represent. I don't know how strong constraint it is. Are there entire classes of shapes?
Well, the only thing is it's creative. Okay, there is no optimization going on. While usually there's some model requires an optimization to learn the hyperparameter, optimize the data. In this case, you don't have hyperparameter because if you remember the function, the only parameter there is this big R, which is the largest pairwise business, right? So that you have to define a boundary and region. Where you say, if these 2 points are on the bounds of this region, they shouldn't not be correlated. Everything in the middle is correlated.
The thing that I keep struggling with is magic. Normally you make a trade. You trade the power of your representation with the robustness, for example. And it seems that you manage to represent anything very robustly, and that makes me think there must be something.
Well, the Gaussian process has been proved to be really fast. But again, we are going back to the discussion about the kernel, right? Because any volume machine learning that uses this kind of explanation then rely on the kernel. So if you are able to find dimensionality of the problem where basically you are able to express this condition, then you're fine. In our case, we tried several kernels, and then we looked into the literature, and we used the printer. Another trick we did was to generate artificial points outside. Because since we get the very first collection point of the object, then you can generate a sphere point that wraps the object. So what you do, you just say, you know what, there is no object outside this sphere, so focus on here. So that's obviously improve the performance of the object. But for example, I also tried the square exponential, and I managed to get results also in that case. But obviously, I tried that for including normals, drop-down, and convex, and of course, in this case, the optimization plays the huge role, because obviously you have mag now, and you see the backside on one side and the front on the other. Then you have to learn something in the middle. There is nothing in the middle. There is a completely function. So, but you can do it without optimization. You actually start getting results where you can actually estimate it to the normal of the object, where you haven't seen anything. So it's pretty strong formulation, because it basically gives you an analytic function.
The downside is computation time, and the way that computation time rises with the number of data points. That's the price that you pay. All these GP methods are incredibly good at inferring a lot from very little data. If you've got a huge amount of data, you'll be there for a huge amount of time. That's really, and so one of the things is at the moment, actually, are you showing the GP model now?
Yeah, Jeremy, I just want to show you that, for instance, right now in the I think you are seeing like a fine mesh. We stop it for a minute, and we're showing the fine mesh, a fine granularity mesh. And just to show you the ability to deal with the zoom out, for the topology. Right now, the Gaussian process is handling both disconnected points, manifolds. One disconnected manifold of two components. So it is because in the let me show you here.
What do you want to see?
If you take a look, the hand is in the middle of the spoon. So there is a part for a manifold of this and a manifold of this, right? There are two shapes for the spoon right now because the hand is in the middle.
Perfect.
It's just to show you the capability of the Gaussian process to deal with arbitrary topology.
And how many touches is it done at the moment?
Well, hard to say right now.
It looks like to me like about 20.
About 5 contacted and several, like about 20 not contacted.
Okay, and it's getting information from the non-contacts as well, right?
Yeah, sure.
Perfect. Okay, Carlos, is there anything else you want to say before we start the next demo? But obviously we'll leave this running so that we can come back to it.
You can warm start the demo and start from the current status. Yes, it's fine.
Run.
I don't hear you well.
Antoine is saying, while we were talking, the robot looked as if it was probing its own hand. Is that correct?
I couldn't see it, but in any case, those paths that collide with the hand are not executed because of collision avoidance. I mean, there is the hand model and the Pro, and they should be discarded by collision avoidance, by the motion planning, right? They weren't discarded. Okay.
They went there, but
I mean, we could just avoid that from the beginning by discarding already the path that collide with the robot model from the start. But the thing is, just to leave it, not to constrain the problem for now, we just left it like it could be also try to explore those points that are close to the robot. Right? All right.
Anything else you want to add, Carlos?
Not for now.
Okay, can we give you a round of applause for the first part of that? And thank you very much. Massive applause for Federico and Gaspare and everybody else in Pisa. Cheers, well done. Well done to Paddy. So, everybody, good. Thank you very much. So,
Thank you.
I'm going to hand over to Amano and Maxime.
All right.
So we're going to shift around here. So we're going to we'll keep watching.
Sure.
But we're just going to start up the other demos.
Perfect.
And what I would suggest you do is just give me a shout if you've got another visualization or something you want to show. And
Good.
we will
Right.
you as soon as I think a good point there is to interrupt. All right? I'll be sitting near the computer.
Right.
Okay. So shall I do the talking, or do you guys? Maxine, do you want to, or my? I could do it before. I could do a little bit of talking around this. Or do you want to do a little bit of talking? How you feel?
You can start.
I can start.
Okay.
Okay. All right. So this is our end-to-end demo. So what we're going to see is a sequence of operations. We're going to see a number of things on the screen. We haven't got another big screen to show, so we're going to have to get around as far as we can. But what you'll see is that we've got a wrist camera on each wrist. We've also got a chest camera. We're not using the head for this particular demo, although we have used it for data sets and various other purposes. So the hand, the wrist is going to go to an initial position. We have localized the dishwasher rack that is beige with the wrist camera, I believe, or is it with the chest camera?
Okay, so basically the task is we localize the rack, the rack on the left with the chest camera, estimate the physical rack with the chest camera, and the task is we want to place the plates that are on the small rack on the right side of the robot on the left rack, the left side of the robot. And that's basically the task.
So we're going to pick up the plates, we're going to pass them, and then we're going to put them down. And so if you start up, whatever the plate required to take the next step. One of the things I can talk about more over here is the fact that if you recall from last year that the rack, when we're doing placement for the product experts, is like the hand. So just as for the hand when we're grasping, we have a mesh model, a tri-mesh model. So what we do is we build a tri-mesh model, a very, very big professionally, rather than so that we can have a very, very big model of that. An extension of the method could be that you would have a point cloud that you get the rack. But also given the fineness of the requirements, you have to be very good. So that's the one thing that we're trying to do. When we're fitting it, we just, as you can see there, we've just got very, very little data return from the point cloud. Right? Very little data return, which we use to localize the rack. So we're actually localizing a very good model, although that we're localizing it very, very well, very, very little data.
Yeah, so essentially right now it's just estimating the position of that. And it will take a little bit of time. So just to get a quick look what's going to happen during the demo, basically just the robot now just assume the default position to start the demo, and after the rack pose is estimated, the robot is going to start to explore the right workspace to pick up contact points and to try to find out what would be the best rack to point in order to pick up the plate. And to pass this plate to the left hand, that's going to perform the placement on the rack. So basically, now the right hand just started.
So now you get a point cloud up on the screen of the plates, which we snip to the bottom so we don't try to grasp the right position of the back and the left. We can use the plates and the up. So now we'll put it as a grasp, which you can see on the screen. So that was the mechanical grasp of the object. The time this is watching there.
What camera are you watching with?
So this right now is this camera on the right. So this sound came from this camera on the right.
Every camera or?
It's a depth sensor.
Yeah.
It's a time sense. Actually, so it takes a few views in the beginning. First, it tries to generate some grasps, and afterwards, it tries to select what is the best grasp that can be considered safe. Because we have enough fancy grid mapping and people fancy mapping in all the workspace of the robot, and then we can try and interpolate the manipulator hand and use workspace, what's the right workspace, in order to see what would be the probability of collusion, and then we select the trajectory that we think the safest is. So it takes a little bit of time, both to update the outcomes with map and then to do all the planning on the workspace box.
Do you have a camera on the top of the or
That camera is not being used. There's been three cameras that are being used. It's only test camera, the left camera, and the right camera. Right now it's just enough.
is there a reason why you're not using the top one? Is there a reason why you're not using the top one?
Basically because we actually don't need it. And it's very difficult because you have a very limited range of scanning, and the quality of the phone calls that you get as father you get from the after one that they decrease.
So one of the things that we discovered is this is essentially our first forest construction, is forest construction Mark 1. We did consider redoing it, changing the concept, so that we can move the arms around, step around, down rather than up, and change the position, get people, which you only learn by sort of doing this stuff. So, but to be honest with you, probably the head is kind of down too high, is really quickly going on top of it the long way around. There are also problems in the sense that the calibration of the cameras has to be so fine, typically the positioning on the head. We didn't need, to be honest, we didn't even try that whole.
Okay, so now it's going to grasp the plate. It likes the plate in the middle because it was safer for some particular reason. The exploring of the workspace. We just found that this trajectory has a bit of collision with the 0.008 in physically.
So up to the point where it's lifted, it's doing all of this active sense active division that Amano's got trying to see that. So we've just seen both the normal graph, the product of experts grasping, it's the original product of experts grasping. Because we asked the school members for a demo, we're going to have to take this as a compositional grasping demo, even though really it's grasping novel objects, but not grasping objects. That's relatively
So now essentially the actual picking task was finalized. We're now just going to the default position again. Now that we move to the passing posture of the robot, it's going just to present the object so that it can be scanned by the left hand. And from this scan, we just use Marek's approach and James as well to generate new graphs to perform the passing. They have knowledge deployment with direct deployment, they take into account the self-images,
At this moment, the left arm knows the location of the right.
no. Basically just
we give an example, you just slow down. I mean, in the sense like collision effect.
No, so it seems that he's thinking now about where he's playing.
Yeah. No, this is completely. What's the order of grasping? Is there something there? he's asking since he's thinking about the position of the point cloud, or do you think about
No, so there's no position at the point. It's just a point. What's the left hand doing? It's left hand. Well, it's just stuck with collecting the point. He's collecting data. Yeah. But he has the possibility to know where it's placed. Because the right hand grasps the plate. Well, it depends what you mean. Yeah, well, in principle, you could transform the point cloud, I suppose, visible to the view. But that would be a possibility. The problem is that in practice, because the VR hand is not strong enough to take move around. Yeah? And so, in this case, we can use some sort of trackers to actually track the movement. And we decided that this does not work. It's just better to get again. And this is not going to be market. You remind me of when you get a game music, and that's scary.
I'll show you this YouTube video.
Every time you make eye contact, yeah, every time you make eye contact,
I'll tell you one of the quotes you made in this video right now. So, more importantly, much more interested in this over here. So, the passing is one of the most. This is a very delicate, it's an extremely delicate operation. I haven't touched it yet.
and this is completely sensor free. The passing. There's no force feedback. No. It's all based on internal values.
I think the force contact detection is.
No, we do force detection when you're placing the plate on the rack.
Whoa.
So when you're doing motion planning, what do you do?
Well, we didn't do the exclusive point.
So what do you do? Do you have to diamond volume around it, or you
Only for the moments when you're trying to grasp, but not in the motion.
and so you just do it like
When one is moving, one gets.
So here there is the sense, as you can see.
Because if you see the problem, it's
Yes. You follow the trajectory until the plate is in contact with them. So when it feels the force, it stops and releases the action. No. I'm saying that if you're holding a plate and you are keeping the plate. No. Indeed, for that reason we scan again, because the lower part of the dish is not seen at the beginning. So when you take it out from the rack, you show it to the camera, and then you complete the point cloud, decide where to grasp it, and go for it. But also when you put it down, it doesn't remember how the shape of the dish, but you realize on the contact.
So it because of that one collision error, the rack moved, because obviously it came down, it touched the rack as if it was putting the plate into the rack and it could feel the contact. But in doing that, as it then opens to release it, it moved the rack slightly. So the rack needs to relocalize, but normally we only relocalize at the beginning of the trial. So we're just going to reset it so that it will at the same time. So you can see
this is I'm learning a lot from what you think you guys and watching this. It seems to me that one of the battles you really have to fight is you have a bunch of sensors giving you a bunch of disparate information coming in. You can see some of it as you cover a long time to process, some of it getting to the machine and trying to sort of interweave the sensing and gathering of sensor data with the execution and the planning, and it just turns out to be a engineering nightmare. Is that good?
this is very
That's really an observation I have.
But the thing is also, is here, particularly in this system, you're looking at I mean, you started to write what, the first line of code you cut in 2004?
Yeah.
But no, but the point, the thing is that the answer to these things is that not only is it a nightmare, but what you have to do is you have to build up a code base that does everything through time. Now, Ross is obviously meant to deal with the numbers, and you can build systems quite rapidly, but it really is true to say that one of the philosophies that we've got is we try to build everything, really in a way. We only take what is really reliable. Now, obviously there were limitations. I mean, that one thing that we didn't check, we didn't put a bounding box on the plate. Okay, so that's completely screwed that whole run. And that may happen again. I don't know. But everything else here is really engineered extremely carefully. Now, you could say that the philosophy of robotics ought to be rather different. You ought to be able to be floppy and all these kinds of things. So what we're still, in the sense of still using quite traditional robot hardware, and that means we do operation right and all these kinds of things right, to do this kind of stuff, and that means it is in some sense critical, and what we're doing is we're taking account of the uncertainty in a different way. Now, the soft hand is at the beginning of a new philosophy, and sort of trying to find this kind of connection between the sort of probabilistic machine learning side and the soft hand side and the planning, all these kinds of things. That's been one of the things that we've tried to explore. It's not in this system, but it's in much of the work we've done. So yeah, but the engineering is horrible, and I can only say that just by watching the looks on their faces, right?
Very different pieces of scientific work. And this is what they are doing, because there are quite a few altogether. We have one compact demo. It's way. So here it's like collision detection. So you have to really fine tune to actually make a copy of each part. Well, otherwise, it's not going to work because it's unfortunately well. If you put a lot of effort into this, like half a year of engineering, you can probably very fine tune everything in the way. No problem. That's going to be. I don't know, and I honestly don't, if I believe that 6 months of engineering will fix this, or if the problems here are really more difficult, it's first problems, and we say they're engineering problems because that's how we see them when they occur. But if in fact there are some fundamental problems that as a community we still haven't gotten our hands on enough, that we'd like to paste over them with engineering solutions, but really there's a huge. I honestly don't know the answer.
For example, consider the problem of expectations. How can you tell which is best? Anything criteria. So we always can find engineering criteria. Let's start in general criteria. What is generally from the data and finding general criteria, find difficult to select sensing action so that you can actually sense happening according to a particular customer. You can put it as an engineering task because sometimes the task is very well defined. That's what but in a general sense, it's something to evaluate.
So, as I said, natural motion within the constraints.
In the sense of the single problem, if you are now willing to
I like the way the two students could put their heads in the workspace to save the demo. That's great.
Oh God, we're in the workspace all the time. If the health and safety officer walked into us in the middle of the night, we wouldn't. Yeah, no, I'm afraid we all. Yeah,
nothing more defined.
So the motion that we just saw, and my question is that an engineering problem, or is that a fundamental understanding of probably the configuration of that problem? And I don't know the answer. I really don't know.
Motion planning is getting more odd actually. Right, Marek, what's your view on that one?
Well,
Is it fun?
You can constrain the motions to some manifold.
we shall see that, for example, that was in markets which are sort of similar to human, for example, trained from experience. But people are doing these things, and that's also good things. But when you do some planning approaches, then obviously sometimes you end up in some awkward movements. For example, for some movies, or some movies, some whatever. It definitely doesn't even want to. We know that actually the 90% of the information is 10%. So from my perspective, this is clearly a scientific problem. Because if it weren't, we'd have methods that can take the box to that work. But when we have a toolbox of different methods, they all work to different extents and have very different properties. And there's no one method that works well in all situations. So it's clearly something missing.
So you said anything else? Motion planning algorithm?
Alright.
The motion planning algorithm is based on what?
This one, this is modified. Some processing. Yeah, no, I think that's what's the novelty. When he says some post processing, there's some. It's basically it's kind of differential evolution, right? Yeah, the high speed of this long. Yes, there are some. This is actually. So yes, so the motion planning ideas are published in his PhD thesis, but they're not published in any journal. So we've never submitted them for publication anywhere. But there's actually some nice ideas in there, which are worthy of publication.
So then another question. And this robot lives in the same work. It never goes through different workspace. There are occasionally some obstacles in the workspace. Why not spend 10 days with computer and do optimal roadmap?
Yeah, this is what it does. But it's just a very quick, not any 10 days, it's at the beginning. It's a static and dynamic function. Okay. So it does this we can be static and dynamic. So there are things which are moving and there are things which are not moving. Now we are following the ordinary path of the This leads us to estimate the context that we should put the play in this way. And the dishwasher is the dishwasher is actually a robotic hand that activates that. You can see that and that the problem of plastic and plastic and that's what actually managed to do. Uh, and right now, that's essentially what's going to be executed. The back is going to blast the plate. But the thing is, as you can see, sometimes it's still not 100%. Also because for many reasons, that might take many different reasons for different objects of the with the friction that was not model. Because there's no functionality in the generated mathematical. There are many factors that are very complicated to make
will have to say that is a downside of the fact that we don't model. Is a downside of the fact that we don't model the graph in a non-object, just modeled by a point cloud, right? You see three plates, you have no idea they are three plates, so we go to just one. And when it comes to there is plates or other points, but we don't model them as an object or in our mesh or whatever. So it's difficult obviously to take into account physical properties of the object and also collision effect.
Did you try to have the object model? Yeah.
But the fact is that our approach is model free. So we want to show the potentiality of doing it without knowing the object. You don't need to learn the object. You don't need to know the object. You just need to scan the environment and take decision. And as you can see, it works. Obviously, then there are all other problems which are engineering most of the time.
I like it a lot, and that's why I like this part.
It's a day. It's a day.
But I promise, if I didn't think you were very smart, I wouldn't answer you. I don't want to say that because I didn't ask questions to everyone today.
Okay.
You're having it pick a plate and put a plate into a map, which means you have a model of it.
Yeah.
So you're willing to give a mark everything except the plate.
Well, but the point is, the fact is that this algorithm can perform, right? So without knowing that. But that doesn't mean that the robot doesn't need to know anything about the world or about himself, like the schematic.
No, in fact, here's my point. You can't make a motion to insert a plate into a rack if you don't know it's a plate. You're not planning a motion of a point cloud so that the point cloud will go into the rack. And so you're planning this. Who am I talking to?
I'm sorry, because we are just.
So you're planning a motion to put a point cloud into.
No, you're misunderstanding. He's saying a point cloud into a point cloud, not we're putting a point cloud into a mesh model, precisely because in this instance, you're absolutely right. The rack is like the hat. And that was how we did the products of expert objects in place.
But still, you treat if we're planning this. I don't. At any point, it's interesting for me to be quiet on what you're saying. The stability analysis that we do for the graph is point cloud and mark.
Yeah, there's no stability analysis strictly speaking. There's only the grasp generation. We don't do any force closure analysis or any of those kind of static analysis for stability. So
you're treating gravity in the analysis of that graph.
No, it's all completely open loop. It's all completely open loop and completely machine learned. So we generate it exactly this probabilistic method. It's memory based because we're saying where did I grasp before? What is the way that I can reproduce the grasp that I experienced before that is closest to that experienced grasp in terms of the local curvature and so on. So no model of the object that you're grasping, no model of the no stability analysis, no force closure, no force sensing except right at the end in terms of we contacted it in this version. So all of that, and obviously when you're putting it in again, although you're absolutely right, the rack has a mesh model. Again, you've got to figure out how to put that plate in, and that here it turns out to be. It seems rather uninteresting, but it's not in the sense that I can put it in this way, I can put it in here, I can put it here. And the whole point is the model understands that those are all different reasonable things to do. So it will generate all those possibilities. Now you don't see that because it's a place, it's a sketch. But there are other ways. So for example, it would know that if we trained it to put a cup, and that we trained it to put a cup on the bottom of the sorry, that's what's so interesting. So 18 months ago, you may remember that we lost a finger, and it was charged to the project. But this is one of the things that makes you really nervous with these. I mean, particularly, this is why the Pisa hand is so wonderful in many ways, because not only is it a fifth of the price, it's also massively more robust physically. But the thing is, if you put, so for example, if you trained it, and we haven't trained it, as we said, for good reasons, but if we trained it to take a, for example, one of the things we originally wanted to do was to take something like a cup and put it onto a spike that you get in these commercial dishwasher bags, and to learn that that's the spatial relationship that you want to have. And it would do that, and then it would put it on any of the spikes, and it would put it around any of it. But the point is, well, yeah, we need to generalize some of the mesh models as well. But the point is that placement is more general than it appears to be. It's not. It has been learned. So all of the interchanges between the objects have all been learned using the product of experts method. So you pick using product of experts, you pass using product of experts, and you place using product of experts. And it's always the receiving it's always the receiving hand, as it were, that is modelled, and then the thing that it's grasping is a massive round of applause. So, incredibly well done. Excellent. So, Carlos, do you have an update for us? Or do you want to show us one in a bit, or should we get on with the vision?
Yeah, you go to the vision.
Okay. So now what I would suggest is that people, you can either stay on that side of it, or you're welcome to come over here now, because now we can safely move the table or something without anybody wanting to kill anybody else. Yeah. It's used to standing quite close to us. This way. So now we're gonna do. So we talked about the stacked autoencoders method, and I highlighted some of the strengths and some of the weaknesses of that. But we said that we'd do a demo where we were covering some 3D structure from the RGB information. So that's what we're going to show you now. So this is all learned. So this is a final one. So we're going to have some. Okay. All right. Good. So.
Marco, sei in diretta.
Sì. Faccio vedere la demo.
Esatto.
Well, it's a matter of so we're not handling fusions in this information. That's something that we do with the construction. That's something although one of the plans has been to use the probabilistic composition model as a food processing step for this model. That model can use the information and from that building some now, using the composition model, ultimately the processing we were starting to with us to which is these kinds of routing
I think it's trying to see something that doesn't seem natural.
Example, take example.
But it's looking at things now, it's putting them into models that can work. You're not building them.
In the past, right? In the past, in which you can't learn the that happens. So these kinds of new kinds of
No, I'm just trying to understand what's in.
I mean, it's something that they can do this. If you explain that, it will find
So the thing is, the reason for the present small was that it turns out that what we want to do is geometry projection from one surface to another. And then string that up. Yeah, so the reason I was trying to explain this morning is that we want to also do practical training with the surface model with the we can do it eventually, but what we found it easy to do is to try and do it this way because it allows you to also get the physics geometry of knowing which part in 3D surface space of one metric corresponds to which feature in 2D to reflect to you. And the neat thing about doing it in this way is to co-train everything instantly, so you basically get all the correlation because you put this training in so many times. So it turns out to be, it's certainly not impossible to do it, but it's technically a lot more work. And given the other things you want to do, we thought this was and we actually started this just at the time we got to this. So you actually work on this stuff. But so we're able to look at data and something about from just the topic seconds and it's a depth number, but we're not using depth, we're just using energy. We really are just using the energy. If it doesn't make you angry, I'm not making it.
Oh, really? You think that?
So, anyway, so that's the first thing. So
But this is yeah, the only thing is
the ball's up the wrong way. That's, it's very. I don't know. Yeah, well, Okay, I think so that was the demonstration. Obviously, that was the main thing that we so this things we decided we're not expecting to be physically possible, but that was our main piece of integration. And also the soft hand grasping, which you get we can show you. But thank you very much again. So thank you to everybody who's done their Carlos, do you have? Is there a last update from Pisa?
Hi, Jeremy. Yeah, the thing is, we had to restart a bit. So this is. Let me show you this is the current view. We can just compute it right now to see what it is. But it's not.
We're watching it growing.
It's not the same exactly. It's not the same run as before. We had to restart it for 5 minutes before. So right now it's computing here. Let me show you.
This is the GPU process running live.
Yeah. Can you turn it a bit? Yeah. This is the generation of the fine granularity generation of the mesh.
And this is after now only a few touches again.
Yeah. The thing is.
1, 2, 3, 4, 5, 6. I can see maybe 7, 8 touches.
Yeah.
Carlos, what is the threshold you're using to print the point?
The threshold we're using is 0.03? 0.1.
Okay, so this means that the point for the custom process has a value between minus 0.01.
Yeah.
This is the value of the value function. Right? It has a threshold of 0.01.
The good thing is that we actually don't need this fine refinement of the mesh for working. This is only by the end of the exploration. So yeah, actually the orange part is close to the handle of the spoon, which is the most uncertain part because it hasn't been explored so far. Instead, on the top, which is the cap of the spoon, where there are already some touches, the shape is starting to look like the cap of the spoon.
Excellent.
Good.
Thank you very much.
Thank you.
Cheers. Listen, guys, I'm really sorry I can't go and have a beer with you.
All right. So we stop the broadcasting now.
You stop the broadcasting now and go and have a beer, and I'll see you soon in Pisa sometime.
All right.
Okay. Take care. Thanks for everything. Cheers.
Bye.